dimensionless analysis, introduction to dimensionless analysis. Okay, this part is for introduction. Okay, what is the objective of this chapter? Is to acquire fundamental concept of dimension. You need dimensional homogeneity and dimensional analysis. So the learning outcomes for this chapter. So at the end of this chapter, students should be able to first develop a set of dimensionless variables for a given flow situation using the Buckingham pi theorem method. And second, express the results of the dimensional analysis in the required form. Third, discuss the primary purposes of dimensional analysis. And last is state examples of common dimensionless number. For example, Reynolds Froude number, friction factor, and many more. So what is dimensional analysis? So the importance of dimensional analysis is in application of fluid mechanics in design that makes the design much more simpler, when you use of empirical result from a lot of experiments. So this data is often difficult to present in the readable form. Even from graph, it may be difficult to interpret. So the dimensionless analysis provides a strategy for choosing relevant data and how it should be presented. So, for example, you want to evaluate or you want to understand about the dependency of a pressure to the pressure vessel. So you have a lot of parameters in order for you to design for the pressure vessel. You might have a density for a fluid, viscosity of the fluid, diameter of the vessel, height of the vessel, and many more. And every one of these parameters, if you do the experimental procedure, you have to determine the effect of pressure to the effect of height of the vessel to the pressure. So you have to test a series or maybe 10, 100, 1,000 different heights in order for you to understand the effects of the height to this to the pressure of the vessel. And and second parameters, you want to check on diameter of the vessel. How does this diameter affects to this to the pressure of the vessel? You might run an experimental experiment for about 100 or 1,000 tests before you can actually measure the effects of diameter to the pressure in the pressure vessel. And then if you have 10 or 20 parameters that might affect to the pressure in the pressure vessel, therefore you have to test a lot of experiment, you have to run a lot of experiment, maybe 1,000. If you have 10 parameters and then each parameters you have to test it about 100 tests, and then times with 10, it might be 1,000 of tests should be run before you know that before you can actually analyze the effects of each of the parameters to the pressure in the pressure vessel. What does the dimensional analysis do is from the 10 parameters, it will reduce maybe 3, 4, or 5 parameters that have not directly impact or directly affect to the pressure vessel. That is what dimensional analysis is all about. And any physical situation can be described by certain familiar properties. So we have length, velocity, area, volume, acceleration, and etc. These are all known as dimension. Okay, dimensions are useless without magnitude being attached. We must know more than that something has a length, it must have a standardized unit such as meter, a foot, a yard, and etc. Okay, dimensions is properties which can be measured. Unit is the standard elements we use to quantify these dimensions. Okay, so the primary dimension in this chapter, we only consider 3 primary dimensions: length, mass, and time. Okay, so this is list of dimension from common physical properties. So take a look at the velocity here. The unit, the SI unit for velocity is meter per second. When we change into the dimension form, meter per second will be m is length, L, and then second is t. So t minus 1 means that L over t. So acceleration meter per second square, if we change to the dimension form, it will be L over t square, or LT minus 2. So here we have some dimensions, and then when we convert or when we change into dimension form, here is the dimension form for the quantity. Okay, you may refer this in your slide, or you may stop this video and see every of these SI unit change into dimensions. Okay, next is dimensional homogeneity. What does it mean? Law of dimensional homogeneity states that every additive terms in an equation must have the same dimension. It means that left hand side and right hand side must contains the same unit. So for example here, as we can see here, Q is a discharge. Okay, discharge. Unit for discharge is meter cube per second. So we take a look at here. If we change B is length, so we have meter. Okay, G is gravitational acceleration. We have meter per second square to the power of third is 1 over 2, power of 1 over 2, and then H is height is M 3 over 2. If we multiply all these units, we will get the same unit as left hand side. So dimensional homogeneity says that left hand side must have the same unit as right hand side. So if it does not have the same unit, so you have to add some more parameters in order to get left hand side and right hand side with the same units. Okay, so that is dimensional homogeneity. So if we change into the dimension, we will get L power of 3 t minus 1. Okay, this is meter cube per second, L to the power of 3. Meter cube, meter is L, power of 3, second is power of minus 1. So this is from meter cube per second. So change into dimension, it will be L power of 3 and t. So if we change into a linear form, so we get L power of 3 t minus 1. So this is the same. So for this right hand side, it is based on the units before. Okay, here we have meter. Meter is length here, L. And then second is meter per second square. So we have L over t square, power of 1 over 2. And then the last one is height, meter. So 3 over 2. So meter is length, 3 over 2. When we multiply all these dimensions, we will get L to the power of 3t minus 1. So this dimension is the same as left hand side dimension for Q. Okay. This property of dimensional homogeneity can be useful for checking units of equations, and then converting between two sets of units. And the last one is defining dimensionless relationship. So what is the importance of a dimensional analysis? First is to generate non-dimensional parameters that help in the design of experiments, physical and or numerical, and in reporting of result that simplify the experiment. Second is you may use the result from the dimensional analysis to obtain a scaling laws. So for example, you want to do a prototype and you want to you've done a prototype and then you want to do to fabricate your own equipment, then you may use dimensional analysis to scale up from your prototype design. Okay, next is to predict trends in the relationship between parameters. And the last one is result will be independent of unit, easier to apply to other similar system. If you get the value, if you get the dimensional analysis result, and then you can apply that result to the other similar system. Okay, in this subject, we will use a Buckingham Pi theorems method in order for us to do a dimensional analysis. So we will use the pi terms in the Buckingham Pi theorem, and this will be explained more on the next videos, because there are 6 steps in order for you to execute the Buckingham Pi theorem method. So you may refer my videos on the YouTube, and then please study on that YouTube video in order for you to understand about the Buckingham Pi theorem method. So in the Buckingham Pi theorem method, we are using a method of repeating variables. We will choose 3 or 2 repeating variables from the listed parameters for a Buckingham Pi theorem. So again, that is I will explain more on the method of repeating variables, which under the Buckingham Pi theorem method, more on the next video. Okay, I really hope that you study from that video on how to do Buckingham Pi theorem method, and by using a method of repeating variables. Okay, thank you, that's all.